Cats and kittens, it's your professor Dr. G here. We're going to go over using SciFinder Scholar. So SciFinder Scholar is basically the Google of chemistry in many ways. And so what you first need to do is get it set up and register. So what you're going to do initially is just use the old Googler to Google it, UT Dallas SciFinder. And you're gonna look for, here we go, slibguides, great. It's that databases, and UTD is generously. And down here you'll see SciFinder. And what you need to do is this part right here. You're gonna need to register, right? If you need safety, I'm sure one of these fine people will help you out, but you gotta register there, all right? And then once you register, then you're able to go ahead and access it. So you would then click this link here, and that would start the whole thing up. All right, so I'm off campus, as right now we all are, thanks to the contemporary plague of Justinian. We have to do this. So we have our net ID and password, and boom, log in. All right, so that starts loading. Various and sundry, weird things pop up here. Username, password, sign in. All right, all that's fine. And you may be prompted for some windows. I assume I was going to be prompted for something. No, I wasn't. All right. Well, there you go. All right, now we're in SciFinder. So SciFinder is really fundamentally the most important thing, the thing that makes it distinct from Google Scholar, which you can do most searches for, and in some ways it's very capable. But the one thing Google Scholar cannot do are these chemical structure searches, okay? And that's going to be something we're going to get into very quickly. But research topic, that works very good. So, research topic, if you wanted to type in something like synthesis of MRI contrast agent, okay? And start going through there, it will find references to synthesis of MRI contrast agents, synthesis, where there are concepts that are separated. And so if we just hit this, we can get references. And one of the things about SciFinder that you can't do in Google Scholar, and this is why it's so cool, is that you can analyze or refine by name. And you can look at all the people who are quite famous in this area. Amy Silvo in Italy, Tom Mead, he's a fun guy at Northwestern. We all know Dean Sherry, of course. He's dean now of the science school, but Dean Sherry is a longtime faculty member here at UT Dallas. And you can refine by different other things. If you wanted to say refine by a publication type, let's say you wanted to look for review. That's publication review. We're going to look for reviews. You do publication type, hit review, refine, and this will allow you to look now for people who have written comprehensive reviews on things that are probably related to synthesis of contrast agents in some ways. So this is a very useful and powerful search engine, and you can even then go and look for your favorite author. These are the. I'm embarrassed to say I'm not sure who a lot of these people are, even though they've written reviews on MRI contrast agents. But the idea is, this is quite powerful. All right. So that's essentially the synthesis or the research topic search, and some of the power that's behind there. Things you can do with a little bit of tweaking in Google Scholar. Now, what's really great are these over here, the substance search. And you can do chemical structure, Markush. And Markush search is when you have a bunch of R groups. They're really useful for patents, or if you have an idea of the fundamental backbone, like you're doing pharmaceutical or work and you've got like a indole-based backbone and you just want substitution patterns off of it. Molecular formula, properties, and substance identifiers. But let's quickly take a look at chemical structure, because this is what I think is going to help you on your particular assignment. And you've got this chemical structure search, and you can do substructure, exact structure, depending on what you want to do. But let's start with substructure to begin with. You just click to open that up. So, yeah, now we're going to look for something. If you want to try to find, let's say you're interested in developing a synthesis, okay? And you know what you want. You want to make a substituted compound that looks something like this. It's a bioconjugation reagent. That's something we use in our lab a lot. And you can just sort of draw it in here. All right. Oh, I don't want to make that. Oh, a triple bond. That's bad. All right, there we go. Bromide. All right. So this is a bioconjugation reagent that we use to span disulfides. And now, if you leave it like this, okay, that's not going to work. But if you leave it like this, all right, and you do substructure search, it's going to find things that have substitution here on those carbons. There's not a lot of other substitutions you can find, but if you're just looking for a structure, right, it'll start searching for structures that are related to that. And you're going to look for analogous structures right here. And it's searching, and it's going to pull up some references, okay? So this is a fairly well-known, and you can see the substitution patterns that are associated with here. And here's an alkyne version, you know, if you wanted to look at different ways that you can prepare it, biological studies, uses, properties, you can see all those sorts of things. And you can even refine it based on properties if you want. You can get reactions, all right? So you can get where this is a product. You can get, so if we just look for places where reactions that make this as a product, here you go, all right? So this is fairly easy. The number of different reaction procedures here that you can find. If you wanted to make these things in pegylated or aromatic, you know, I guess there's a patent there, so you want to look out for patents if that's what you're interested in. And there are a bunch of different ways that you can do this, and this is a really nice cross-coupling reagent where you have sulfur. So I mentioned bioconjugation, but the crux of this is if you were to start looking at the thioaryl, you can start looking at these things. And so what is this? This is probably, I don't know that reference. But that doesn't make any difference, all right? Now, let's say you wanted a specific synthesis to that, or you wanted to know how to make this compound, right? Or let's say that, sure, okay, let's just say we wanted to make this compound. This is what we're going for, all right? That's what we want to make, and we're going to start with something known, all right? We're going to start with, let's say, I have this in the lab. I'm hoping I can make it using this starting material. Seems like if you reach back to your sophomore CHEM days, that all you have to do is throw in bromine liquid and, you know, a little of that sophomore charm. There you go. We can just delete that there. And it'll come together in 900% yield. But we'll see. All right. So what you do, if you want to see what the reaction conditions, that'll take you from starting material to product. You come over to drawing editor, and you select reaction. All right. And then you draw an arrow, and the stuff on the left side becomes the reactant, and the stuff on the right side becomes the product. And then we're going to be generous. We're going to say substructs of more complex structures. So it's just going to throw substitutions onto these things, hoping that we find something. And then we hit search. All right, there we go. And then that's great. So there's actually a number of transformations. This one seems peculiar. Yeah, really? Okay. Well, that's interesting. I see it. Oh, okay. Well, this is probably the one we want, right? So this is liquid bromine dichloromethane at room temperature, 2 hours worth of reflux. Well, that's actually much more gentle than the way we make it in our lab. We actually use a pressurized stainless steel autoclave, heat it up well above its boiling point with a blast shield. But you know, if this is high yielding, which it doesn't really give you a yield, but let's say we now want to delve into this. All right, so here is our reference. Amyloxylamines for cysteine modification, disulfide bridging. All right, this is one of the original papers, actually. We can pull that up. All right, here we go. And it's got, yeah, James Baker. That's the guy that started it. And we can go to get related, link to other sources. That's what we want. And then that's going to pop you out to where you can download the file. If you're on campus or you have received that email where I showed you all those ways you can access references using various different internet tricks, then you can just go ahead and download this. I think you can go through this sort of peculiar system 9 times out of 10. For me, something happens where it doesn't work. Sometimes it works. Like for some reason right now, I click on it and the little blue bar is just kind of farting there doing not much going on right now. So that didn't work. But this, you know how to get to this. All right, so now you've got it. Usually what you can dig up is supplementary information. And the supplementary information will usually pull up synthetic conditions. That will allow you to then synthesize these if you just start scrolling around. Depending on, James Baker's a really good chemist, so his SI, so you can tell if a chemist is worth anything. Their SIs are comprehensive, and they essentially are basically works of art. And these are not bad. He's a top of the game. So that's basically SciFinder in a nutshell. All right, so that'll mostly get you to where you want. Now, let's say you wanted to reanalyze by reagents, and you could find things that involve piperidine. I'd probably not do that unless you really want to screw with the, well, these are the ideas. All right, so you can really actually play around with this, find publication years. If you wanted to find more contemporary things, if you wanted to look for authors that were involved in this particular research, you could probably do. Wow. These are not the authors I would have expected to pop up. But it's just, it's pretty fun to find out what's going on in these particular cases. So one last little thing, all right? Let's say we're going to continue with this. This seems like a very popular reaction type. And we'll continue along the lines of, let's just look, all right? So we popped up a little thing here about analyze. But you can actually analyze by product yield, which is actually really quite cool. So, if you're very interested in just slogging through some hardcore purification, you can go find this really bad, low-yielding, probably honest synthesis in organic biomolecular chemistry. And then you can come up here to greater than or equal to 90%. And, probably a little bit of science fiction going on. Oh, no. This is okay. This makes sense from my recollection. What is that? All right. That's not much of a transformation at all. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Good job, SciFinder. Those are exactly the same. And it's 100% yield. Wow, awesome. So, you can do a lot of analysis and refinement. Number of steps, that is a super important thing. So 9 steps? Wow. All right. So you can really take your time, if you've got no big hurry to get to this. Oh, that's a very nice looking, novel drug conjugate. All right. Very cool. Very, very cool. You can really put that on some disulfide probably. So that's a good thing to look for. Just through the refinement in the analysis. You can also go through here and you can specify product yield or number of steps. Humbly, honestly, for most things, if you know what you're going to do your transition, you want to look for the fewest number of steps. That just seems to me to make the most sense. Now, there's one last thing we're going to get into just in case you're super curious. What if you didn't want this to be a carbon? What if this was going to come out and be something else? Like a lot of those structures just for carbon-carbon. You can actually come up to this, right? The variables. And you can select a halogen, a metal, any atom except for H, all right? Any atom except for C and H. So this is going to make this a heteroatom. So we should get reactions that put a heteroatom, start with a heteroatom and end with a heteroatom. I don't know if this is going to work. Let's give it a shot. Sometimes you can be adventurous and a heteroatom, hey, what do you know? You can actually start off with with an alcohol. All right, so see, here's the trick. Remember, I started off the original reaction with hydrogens here. I did not specify. Now, if I wanted to really make sure that there was no substitution here, what I would do is come down here. See, right? I implied there's hydrogen. SciFinder does not make that implication. If you leave any ambiguity, it will assume that you are interested in any sort of substitution. So now I've made it quite clear that these are going to start with hydrogens and they're going to end with bromines, and it's going to have a heteroatom here, but not here. As you know from sophomore organic chemistry, halogenation of these things usually occurs under pretty harsh conditions. So if you start off, you're going to end up with a mess, which is why you probably don't see very many reactions of that sort, right? So you're not going to have any luck in that particular on that particular process, which is interesting because we can be 100% sure that somebody started with this and ended with the alcohol here. All right, and that was probably 2 steps. SciFinder just sometimes isn't smart enough to really get that. But you can play with it. I would encourage you to do that. If you need to know how to get to there, what you can do is you can start just deleting things. You can call that. You can still call this a product. You can get rid of that. In fact, if this is your product, this is what you know, you can just come up here in a drawing editor, do it as a reaction, and click OK, and then just select that's going to be my product. That's something I want to make. All right. And a substructure. So obviously this is a substructure guide. They've got a variable Q here, and I can hit search. And so now you're going to be able to find some reactions that will get you to something that has a heteroatom on this particular position. So this carbamide structure here. So you get the idea, right? So anyway, that should be a sufficient amount of information to help you initially scour SciFinder for some data, for some results. A lot of these you can really get through, and you want to find the references, all right? And if you can find those with some of these, sometimes it's not clear. If you want to say collate references, so for all of these things, you have a number of 25. You can actually hit get references, and then that'll convert all of these things into like the references, right? And then you can really start looking at who is involved in the production of these things. James Baker's obviously at the top. You can show some more, and there are people that have been producing these for a while. Okay, and then you can then refine these references based on author and document type and stuff like that. All right, so that is our screencast for the day. Best of luck, and I hope you have a good and safe